So what we're going to talk about in this video is one of object-oriented programming's most famous design principles called solid design principles. So solid is actually an acronym describing design principles for creating object-oriented programming systems. By committing your code to these principles, you will naturally build systems that don't only work perfectly, but also work elegantly. So, as an acronym, briefly, these five are: S stands for the single responsibility principle, where objects should have cohesive and complete responsibilities. It shouldn't be aware of knowledge it doesn't need to be aware of, and it shouldn't perform responsibilities that are irrelevant from it. O stands for the open closed principle, where, where classes should be open to extension and closed to modification. Instead of changing the form and behavior of an existing class, you should extend the class instead. L stands for the Liskov substitution principle, where substituting objects by their subtypes or realizations should always work. I stands for interface segregation principle, where a client shouldn't be forced to implement methods that it doesn't use. Finally, D stands for dependency inversion principle, where object relationships should depend on abstractions instead of implementations. Starting with the single responsibility principle. So, uh, objects should have cohesive and complete responsibilities. I'm just going to repeat what I said a while ago. It shouldn't be aware of knowledge it doesn't need to be aware of, and it shouldn't perform responsibilities that are irrelevant from it. So, one of the canonical examples of violations against the single responsibility principle is the concept known as God class. A God class is a class that basically contains all the attributes and methods of the whole system itself. You'll recognize these God classes as those classes that control the behavior of objects. And they also contain the implementation of client objects' behavior as well. We call these God classes because they are omniscient and they are transcendent. They are omniscient because they know knowledge they shouldn't be responsible of. They are transcendent because they are able to control things that they shouldn't be able to control. These God classes are also aware, again, of all of the object secrets. They expose and manipulate private attributes and methods. So, to look at this example right here, by the way, before you listen to this, before you watch this video, you should have completed two lab exercises. The first one is the library card or the borrowable item exercise, and the second one should be the bank system lab exercise, because we are gonna allude to those exercises. So here's one. I'm using it as an example. So you have here as an example above, or this as an example here, the library card as a God class. This one is a God class since it exposes the secrets of one of its client classes, such as date, for example, and it exposes it through these evil getter functions like get month, get day, and get year. So these are evil getters, and getters are almost always evil since uh, a function that gets something would almost always be a violation of the privacies of those private attributes. So getters are inherently evil because they are kind of counterintuitive to the existence of these visibility modifiers like private and protected. So these attributes like month, date, and year, which are supposed to be private, end up being revealed to other classes because of these getters. Get month will get the value of these otherwise private attributes. And library card, the way it uses, since you notice right here, is a this is a usage or a dependency, an aggregation relationship. It is merely a user of the date class, but it is aware of its secrets, its private attributes, month, day, and year. These ones right here. So although it isn't obvious, it also tampers the responsibilities of borrowable item as well by deciding by itself how penalty is calculated for each realization. So you have right here an example of how it implements borrow item, which is a bad implementation of borrow item. What you're seeing right here is it calculates the penalty right here. This snippet of code is a calculation of which day it is. It calculates it using the get day, get month, and get year evil getters because it tries to uh, expose the secrets of date. So another violation right here where it decides by itself how the penalties of book, periodical, and other realizations for borrowable item, how they are calculated. So what it does is it has this if else check right here. If B is an instance of a book, then it borrows it in the same way a book is borrowed, something book related. Else, if B is an instance of a periodical, then it does something periodical related, borrows it in the same way a periodical is borrowed. So this instance check right here, this exists in a lot of object-oriented programming. In Python, you use this function instance, for example. Oops, that's not the right spelling. Instance of book, for example, this will return what is the instance. Oops, not B, book, but B. It will return whatever instance it is. And Java, I think you use this keyword instance of B instance of book. This will return either true or false if B is indeed an instance of book. So once you start checking for the exact type of a specific borrowable item, you should already consider refactoring your code since introspective checks like is instance, instance of, type of, and etc., are symptoms of smelly and bad design. You can think of these instance checks as analogies to racial discrimination since your client object asks the race or the type of the dependency. What is going on right here is some sort of discrimination because library card is has to ask this instance B right here. What is your exact type? What is your exact race? Are you a book? Because if you are a book, I'm going to treat you this way. If you are a periodical, I'm going to treat you another way. So again, these kinds of checks, whenever you find yourself doing these, you should consider changing your architecture, change refactoring your code because that is a symptom of uh, not good design. So what should you do? You should, to fix all of this God class bad designs, you should think about assigning the correct responsibilities. So when you're introducing new behavior or information to a system, you should always ask yourself this question first. Who should be responsible of this behavior of information or information? So, for example, when you're calculating the differences of days to be able to correctly calculate uh, what is the penalty, for example. So you use this part right here to calculate that. You should first ask yourself, who should be responsible of calculating the differences between dates? It shouldn't be library card who should be responsible of that because library card is just a library card. It is just meant to represent uh, what are the things that are being borrowed. It should be able to borrow things, return things, and etc. So what should be responsible about this behavior is the class date itself. A date would know how to subtract it with other dates to get how many days are in between this date and this date, for example. So instead of doing that, you will remove this uh, God class behavior of controlling the date and this God class behavior of forcing date to implement getters. What you should do instead is do something like this. D dot difference, for example. So D again is of type date. You see that here. D dot difference. And you compare that with another date, for example, B dot uh, I think total penalty. Oh, that's not total penalty. That's incorrect. So for example, b dot uh, borrow date. When was this borrowed, for example? So here, you just have to call a function inside the date class called difference, and it will calculate for you the difference between these two dates, the difference between date d and the other date b dot borrow date, for example. Doing this will forego, will remove the requirement of these evil getter functions, since you don't have to know the exact month, day, and year of this specific date. You just have to know that this is a date, and then you just have to invoke the difference function of that date. And date will calculate the difference for you. How many days are between that? Call d dot difference. So this can be removed as well. Second one, who should be responsible of calculating the penalties of specific borrowable item realizations? It shouldn't be library card who should do that. It should be the borrowable item realizations themselves, because different borrowable item realizations have different ways of calculating penalties, for example. Because a book, for example, might have a bigger penalty per day compared to a periodical. And in fact, the way you calculate their penalty could be way different, because, for example, a book's penalty when you return it late could be dependent on the number of days that you are late in returning it. While a periodical, for example, its penalty could be a flat number, a flat rate, just this amount. No matter how many days you have returned it late, this would be the amount that you have to pay for. So since there are, or it is a possibility that there are differences for the way you calculate penalty, then these penalties right here should be methods of specific borrowable item realizations themselves. Inside your class book, inside your class periodical, they should be the ones to implement penalty, because it is different for each borrowable item realization. In fact, knowing that penalty is a requirement for any borrowable item, you can in fact add a new abstract method, penalty, right here inside your borrowable item abstraction, so that all borrowable items are required to have a penalty function inside them. And when you do that, you don't have to introspectively check if B is a book, if B is a periodical. You don't have to create this if else checks, because all you have to do is just to calculate B dot penalty. And library card wouldn't even have to know which exact uh, borrowable item type this instance B right here is. It just knows that it is a borrowable item. So that is the best implementation of the system right here, that removes these God classes, that adheres to the single responsibility principle. The date class should be responsible of subtracting, oops, the date class should be responsible of subtracting dates and adding dates, not the library card class. Forcing library card to contain code for date operations will also force you to break the boundaries of your classes, forcing you to create evil getter functions to expose private attributes, defeating the reason of having these these visibility modifications, these visibility modifiers for attributes. So library card should not be aware of how dates are subtracted to be able to subtract dates. It should only call d dot subtract, for example, or d dot difference. That's the example that I used here. So the same is also true for a borrowable item's due date. The library card shouldn't contain the specifications as to how borrowable items calculate their due date. In fact, library card shouldn't even be aware of the exact type of the borrowable item. Introspective checks like is instance of, these checks that try to infer or try to tell you what is the exact realization of this borrowable item, are symptoms of bad design. It violates this one. So this process of designing these cohesive systems require not only OOP design techniques, but also domain knowledge. So to be able to properly uphold the single responsibility principle, the designer of the system should also know how a library system operates so that he or she can accurately simulate the responsibilities on code. You can also apply the single responsibility principle on individual methods inside objects. So, single responsibility principle, this should also be kept in mind when you're designing how methods, what is the scope of a method? What should a method specifically do? Methods should be responsible of exactly one thing only. Keeping methods pure like these will help reduce unwanted side effects. The builder/manipulator naming scheme will help you with this. Also, a method should not be responsible of handling the problems. This method should delegate that responsibility to the clients of the method. So you notice right here, just by thinking about the single responsibility principle, you will automatically or you will naturally force yourself with these good design principles for OOP. So the builder manipulator naming scheme is actually uh, a good outcome of adhering yourself to the single responsibility principle, since creating the builders and manipulators will force you to create functions with singular responsibilities. A builder should only return a specific value. A manipulator should only manipulate a specific thing. At the same time, whenever you're implementing uh, exceptions and when you're trying to delegate who should be which at which level of your system should a specific error be dealt with, then all you have to do is just think about the single responsibility principle. Who should be responsible of responding to a specific exception or a specific error that was raised by some some component in your system? Should this specific error be dealt with in this level, or should this specific error be dealt with somewhere else? All you have to do is to think about the single responsibility principle. Who should be responsible to do that? That should be the one who should catch that error, who should deal with that error. And that's the single responsibility principle. Moving on to the O part. This is the open/closed principle. So a good class in OOP is both open and closed. It is open for extension but closed for modification. So instead of changing the form and behavior of an existing class, you should extend the class instead. To understand this principle right here, let's have an example of a system that is closed for extension. Here's this is part of the series of solid design principles, but presented using motivational posters. Some artists/computer scientists did these. So open class, closed principle. Open chest surgery isn't needed when you're merely putting on a code. What does this mean? So here's an example of violation for the open closed principle. So this specific system right here is open for modification. So forgive me, by the way, for these long Java-like method names. I have to name them in these long descriptive names so that I don't have to explain what they do. Just by looking at their name, you should be able to guess what they do. Apply all monthly changes will do exactly that. Deactivate if under balance will do exactly that. I'm naming them that so that I don't have to write the contents of these methods. Okay, anyway, so this is a system that indeed works perfectly. The bank will be able to apply the appropriate changes to the account types because of this if-else blocks that segregates the accounts based on its type. But since we've talked about single responsibility principle, you would already say that again, this is a symptom for bad design because this is segregation again. This is racial discrimination. So the problem with this specifically is that whenever there are changes regarding to the monthly changes or interest calculations for each account type right here, you would have to tamper with the contents of the bank. This is opening bank up for modification. For example, if the way you up, if the way uh, a credit account changes every month is modified because let's say the people who are telling you to the bank which this system will be used for will change policies, for example, then you have to change the logic of your code. You have to change the business logic. You have to change how a credit account is changed monthly. Let's say the credit account will have some sort of balance thing, for example, similar to a debit account. I'm not sure if that thing makes sense in the real world, but let's say it does make sense. Let's say it should be deactivated if it is maxed, for example. That doesn't make sense, bro. Let's imagine a parallel universe where that happens, for example. So if a credit account has to be deactivated if it is maxed, for example, then you would have to change bank. You would have to add an extra line here. Uh, Deactivate if maxed, etc., or whatever you should write right here. So modify this part. So every time there's a change related to monthly updates, you would have to do some kind of surgical procedure on bank and rearrange its internal organs so that the change may be supported. So whenever there is a policy change like that, let's say from now on, debit accounts will not be deactivated if they are under balance. So you have to delete this part right here. And every time you do that, you have to look at bank. You have to open it up. You have to perform surgery with it. So this is actually extra rough on bank because bank shouldn't even be responsible for these behaviors. In and of itself, this one right here is already a violation of single responsibility principle. So if there are new types of account, Pajud, then you would have to open up bank again. For example, there is a new special account for this bank. Let's say this is a premium account that has a lot of perks and etc., where the monthly interest is applied every 15 days, for example, or uh, let's say that doesn't make sense. Let's say this one right here never deactivates as well, and it adds a flat amount of money every month. So what you have to do, you have to operate on bank again. You have to open it up and add a new else if clause right here. Right here, else if A is a premium account, then you have to do these things, blah blah blah, right there. Again, opening up bank for modification. And poor bank because who knows how many more new types of accounts there will be in the future. So we know that this is bad design. What should we do? Instead of rearranging the organs of your classes to accommodate every change of policy, every change of behavior that they are not even responsible for, you should close the classes for modification and open them for extension instead. What does this mean? So this is a good example for this architecture right here. Since apply monthly change is an abstract method for account, all its realizations are required to implement it. So what you do instead is you create this realization called account that was not present in this previous example right here. You just have different types of accounts. Now you have this abstraction called account, and it has this apply monthly change abstract method right here. This one should be an abstract method. This one should be italicized, by the way, but I forgot to do that. So since apply monthly change is an abstract method of account, all of its realizations are required to implement it. Therefore, apply monthly change is also present inside each of these realizations right here. Oh, that's not it. It's this one and it's this one. This is a different apply monthly changes. This is apply all monthly changes DI. This is consolidating all of the accounts and then applying all monthly changes at the same time for every account that is associated to this bank. So we extend the functionality of credit account, debit account, and payroll account by adding adding an extra method. So inside credit account dot apply monthly change, So for credit account, for example, you just have to call apply monthly interest. I'm just gonna shorten it to that, since that is all that happens in a credit account. A debit account, inside apply monthly change, all you have to do is apply monthly interest and deactivate if underbalanced. On payroll account, since it doesn't change every month, inside apply monthly change, there should be nothing at all. So is a method that does nothing like this in Elegant? You have to create apply monthly change and write pass inside there. Well, it's not really inelegant because this is actually an accurate representation as to how a payroll account changes every month. How does it change every month? It doesn't. It doesn't change at all. And in the future, uh, the inertness of payroll account, how it changes, how it is updated every month, may be revised due to bank's policy, for example. So at least you have this function prepared right here. So whenever the bank changes policy, and let's say the payroll account can now have interest, then all you have to do is change that and apply monthly interest. So the previous library card example and bank examples are actually indeed similar. This is because introspective checks like is instance are again symptoms of inelegant design. Both of them are violations for both SRP and open close principle. So another example of this is how you need to augment the payroll account class to contain the receive fund float and the deposit float method to uh, facilitate the deposit, the receive transactions so that it becomes a recipient for transfer, for example. But this is the example I'm showing you for now. Okay, a little caveat right here. Closed for modification does not mean you cannot change anything literally inside the class. Of course, if there are mistakes in specific behavior of the class, if there are new policies that you need to incorporate in your system, so you need to reflect that in your software as well, then of course you will be forced to change the specific behavior of the class. But uh, you should adhere to solid design principles, to specifically open close principle, if ever you're incorporating changes that may happen in the future. So if you already foresee the future that there may be new types of account, if you already foresee the future that uh, this kind of check right here might have to be edited since you have to add an else if right here, then we already know that this is bad design because we will be forced to change bank itself for the modifications of other classes. And that's open for extension but closed for modification. Moving on to the next solid design principle, this is what L stands for, Liskov substitution principle. Substituting objects by their subtypes or realizations should always work. So if it looks like a duck and quacks like a duck but needs batteries, you probably have the wrong abstraction. This principle right here basically dictates when should an object be a subtype or a realization of another object. Should payroll account be a realization of account? If you can, this is the rule of thumb right here. If you can substitute any instance of an account with a payroll account, then the answer is yes. So for example, if your architecture looks like this, for example, you have here an abstraction called account. I'm gonna write an I right here to signify that it is an interface or an abstraction. And let's say one of its realizations would be payroll account. So you should always wonder if this is the correct relationship between them. Should account be a realization of payroll account? And the way or the rule of thumb that you need to do to check if this is the correct realization is, for example, you have an instance of A. And this A right here will interact with your system like an account. or if you write this in Python, the type annotation would be written like this: a colon account. So since this is an account, replacing a right here with a payroll account instance should also work as well. So if a is a payroll account, if doing this replacement doesn't break anything in your system, then this established relationship right here is correct. And sometimes the Liskov substitution principle is not really uh, not really invoked. We don't really think about it because sometimes the realization relationships and specialization relationships are obvious if you uh, think about how you should simulate the whole system in code. So the same is actually also true if you want to establish an inheritance relationship between account and payroll account, because you could also, another perfectly correct implementation uh, of this system right here would be, instead of making your account an abstraction, your account could be a concrete class and make this relationship right here a specialization relationship. Then this replacement right here, this substitution should also work. Replacing a payroll account or replacing an account with a payroll account should also work. Replacing a super type with its subtype should not break the system. So this principle right here, the Liskov substitution principle, is very important because it ensures that the polymorphic capabilities of your realizations and specializations are correctly implemented. So while we're here, which relationship is better, realization or specialization? So this might be a question that you ask yourself when you're implementing the payroll account, debit account, credit account to account relationship. So you have two perfectly correct answers for this one. One is better than the other sometimes. And which relationship should it be for these? Should it be a relationship like this, which is specialization, payroll account, debit account, and credit accounts are specializations of account? Or should you make it so they are realizations of your account? So the answer to this question is very situational. And uh, if you need a lot of code to be inherited to your subtypes, if your account, for example, if all of the account types have a lot of common behavior and attributes, you might be better off with writing specializations to save code duplication. But if you know that uh, these three types are different from each other, even though they are under the same account type ontologically, then you might be better off with a specialization relationship. But some people would say that you should always specialize if possible. If it is possible, oh, sorry, that's incorrect. Let me rephrase that. Some people would say that you should, as much as possible, always uh, create a realization relationship between two classes, because a realization relationship is a much looser relationship. Meaning, uh, a realization relationship, for example, this is an abstraction and this is a realization, a relationship like this is less dependent on each other. Because if you think about it, you have another relationship right here, this generalization and this specialization relationship. A specialization relationship is actually quite dependent on the code of generalization because it has to depend on the things it inherits from generalization. Meaning, uh, changes to the generalization class right here will affect the specialization class because there are things inside the generalization that are implemented by your specialization. So that is the dependency between them. some of the code and specialization, you can think of it this way, are found inside the generalization. So if you don't want that kind of dependency between these two, you can create a safer, less coupled abstraction realization relationship right here, like this one, because there is no code in realization that is found in abstraction. You will be forced to implement all of them. Okay? But one of the disadvantages of abstraction, for example, would be if you have another realization right here. I'm going to call this R2, for example. And if this one, if R2 and the other realization R are quite similar from each other, then there would be a lot of common code between them. And since you have established an relationship between R2 and A, as well as R and A, then there would be a lot of common code that you have to write both for R2 and R as well. There would be a lot of code duplication between them since they are very similar. If you implement this as a specialization relationship, the code that is common between them could just be written in the generalization itself, and there would just be only one code that represents both of them. So those are the things that you have to think about. It is based on context, and sometimes one is not really better than the other. It sometimes goes down to opinion on what might your system look like in the future. Will there be a lot of differences between different realizations, or will these specializations remain common to each other? Will they be similar to each other? So asking yourselves these questions will tell you which exact relationship should you create for them. So moving on to the next principle, this is what I stands for, interface segregation principle. A client shouldn't be forced to implement methods that it doesn't use. And sometimes the subtypes or realizations of a certain object may have diverse functionality. Some subtypes or specializations can deposit while some subtypes can't. And all subtypes can be recipient for transfers, but not all can be senders. So this is uh, an example of this is this one right here. The different accounts have different capabilities as well. So some subtypes can deposit, like debit account and a credit account, for example. They have some kind of deposit mechanism with these two, but payroll account doesn't have that. When transferring, so credit account, debit account can transfer, but payroll can. But all three types can receive. So you have to think about these diverse functionalities right here. Some subtypes can do that, other subtypes can't. And if you have a lot of combinations of these functionalities, then you have to think about where should I place this? Should this be placed inside the generalization? Should this be placed inside the uh, the specializations? And what would happen if I implement a realization relationship between these types? So the diversity of functionality support may sometimes force the designer to pollute the system with methods that the subtypes don't actually use. So for example, if you want this to look cohesive, for example, then you might be forced. Let me create a diagram right here. So if you have here your interface account, for example, your abstraction account, and you have the three realizations. This is payroll account. This one is debit account. This one is credit account, for example. And there might be diverse functionality between them in the same example that I gave you in the MP, right? So for transfer, what should you do? Should you if you place transfer here in the account, then all of them will be forced to implement that as well. So you have to write an implementation for transfer here, an implementation for transfer here, and another implementation for transfer here. You will be forced to do that because you have named transfer to be an abstract method. And sometimes you have to do that because you want all account types to seamlessly be able to transfer. So what do you do inside payroll? Should you raise an error whenever you transfer? Should you leave transfer empty? Should you write a message that the transfer is not successful because it is a payroll account? So you will be confronted with these types of problems. Uh, what about when you are depositing? Only some of these account types will accept deposits. So debit does accept deposit, credit accepts deposit, but it's not exactly called deposit, right? Payroll doesn't accept deposit. So if you write deposit as an abstract method right here, you will be again confronted with the decision of what should you write inside deposit for payroll? Should you raise an error? Should you print something? Should you force it to fail, and etc.? Payroll account will be forced, or you as a designer will be forced to pollute the system with these methods that the subtypes don't even actually use. Payroll account will not use deposit, but since it realizes account, you reluctantly add it. So this right here is a violation of Liskov substitution principle, which states that an object should not be forced to implement methods it doesn't use. So what is the solution for this one? The solution for this one is role interfaces. So this is a very complicated looking diagram right here. But the best way to design these diverse systems is by refactoring your architecture to have diverse role interfaces. So these are interfaces that identify specific roles themselves. So instead of having 3 accounts that realize one account, you have intermediate role interfaces right here. You have depositable accounts, transfer sender account, withdrawable account, and transfer recipient account. And if you notice the relationship right here, these are abstractions that realize the account abstraction as well. So these are realizations of the account. And what you place inside account are all of the methods that you are sure, you are certain should be present for all account types, for debit account, credit account, payroll account, and all future account types. So for example, you are sure that all account types should contain the balance report method. You are sure that all account types should contain the account info method. And you are sure that all account types should contain the apply monthly changes method. So you place them into account. So your depositable account, transfer sender account, withdrawable account, and transfer recipient account are all of the methods that may or may not be implemented by your concrete classes right here, your concrete realizations. So depositable account right here will only contain one method, which is deposit. And this is the reason why we'll call them role interfaces. It has just a specific role. It has one role, which is to deposit. A transfer sender account has one role. It is the transfer from one account to another. Withdrawable account, it has one role to withdraw money. Transfer recipient account, it has one role, which is to receive fund. So once you have built this architecture right here, debit account, credit account will just choose which role interfaces does it implement. So for example, debit accounts, what functionalities does debit account support? It supports the depositable account, it supports transfer, it supports withdrawal, and it supports receiving funds during a transfer. Meaning, debit account will realize all of these 4 role interfaces. You'll notice there is an arrow from debit account to all 4 of these. Meaning, debit account will be forced to implement these methods right here, and it should also be forced to implement all of the methods that it realizes as role interfaces. So it will be forced to implement deposit, transfer, withdraw, and receive fund. On the other hand, you have credit account right here. And what are the capabilities of credit account? What transactions does it support? It supports deposit, it supports transfer, it supports withdrawal, and it supports transfer as well. So it will implement all of these four role interfaces. Therefore, you will be forced to implement all four as well: deposit, withdraw, receive, transfer. Finally, payroll account does not support deposit. It also doesn't support transferring as a sender, but it does support withdrawing and transfer recipient account. Therefore, you only see two arrows that come from payroll account. So you can withdraw, you can receive. So the role interfaces that it realizes are withdrawable account and transfer recipient account. So the beauty of this one right here is that you have different levels of roles. The most general roles are placed inside the account. And these are the roles that you are sure to be implemented by any account type and any account type in the future. So these abstract methods right here will cascade down to the realizations right there, meaning you will also be forced to implement them. Balance account, apply monthly, balance account info, apply monthly, balance account info, apply monthly. All three of these will be implemented as well because uh, debit accounts are implicitly accounts as well. But you also have the added feature of implementing optional capabilities like deposit, transfer, and withdraw. They are not necessarily present for all accounts, they are only present for some accounts. So instead of cluttering your realizations with useless methods, you now have cluttered your system with role interfaces instead. But this is a benevolent kind of clutter. This is a good kind of clutter because more objects and looser dependencies make for a maintainable and therefore elegant system. Because in the same way a language with more words have less chances for ambiguity, a system with more classes and more role interfaces have less chances of implementing methods that are forced to fail. You have less chances of implementing methods that don't actually do anything at all. So, because of this clutter, you can have rich polymorphism without sacrificing interface segregation principle. Although you also have to be careful not to overdo it because you wouldn't want a role interface for every conceivable method out there. For example, you don't have to create a balance report, a role interface to represent the role of balance report, for example. So I don't know what you should call this interface right here. You might call this balance reportable. And if you do that, that might be unnecessary because if it is something that is implemented by all possible accounts, then you might as well just place that inside the most basic form of the abstraction, the account itself. So when you have role interfaces like this, you can even refine lines of your code by describing which exact role interface applies. So for example, if you see transfer right here, the definition for transfer has now changed. So before that, transfer accepts the amount of money and it also accepts a recipient of type account. But now you can now refine the transfer recipient to be the specific type called transfer recipient account instead of your general account because uh, which accounts can only receive transfers. The accounts that can only receive transfers are those that are of type transfer recipient account. So you have refined your type system to be more specific as well. In the same way, a language with more words is more specific because you don't have to be confused about multiple words that have different meanings. You have different classes that have different roles, or sorry, different interfaces that has different roles. Uh, and it doesn't really change or it doesn't really affect the system in a negative way because a transfer recipient account is still an account itself due to polymorphism. Because a transfer recipient account will realize, you see this relationship right here, account as well. So a credit account, for example, it is able to be transferred to, meaning it is able to receive funds. Then that means that your credit account is both a transfer sender account and an account as well. and it can behave in the manner a credit account behaves. You have multiple levels of polymorphism in this case. So that's interface segregation principle solved by role interfaces. The last principle right here, this is what D stands for, dependency inversion principle. So object relationships should depend on abstractions instead of the implementations themselves. The relationships between objects should be defined by surface instead of their interior. And this goes back to the philosophy of the paradigm itself. This means that how a bank, for example, interacts with an account should not be dependent on its implementation. So the way a bank prints the balance report, for example, uh, should not be directly concatenating something like this. For example, if you want the bank itself to be able to print the balance report, you shouldn't do it like this. Your balance is space and then concatenate it with account dot balance. Bank should interact with an account by printing the return value of the abstract builder method balance report. This is the proper way of doing it that adheres to dependency inversion principle. That's wrong. This one is correct. Or this one is better. Or instead of actually writing that, you can just write balance report, or you can just call this instead balance report of a specific instance, let's say B, for example, or let's say A. It represents an instance of an account. A.balance report will print the balance report for that specific account, meaning your bank will just have to call A right here in the same way it interacts with any account. It should be interacting with specific account types using its interface. Banks should see account types not with its specific realization type. It shouldn't interact with this instance specifically as a payroll account or a debit account. It should implement it specifically just like any other account. The problem with the first one right here is that account.balance, for example, may not even exist for other account types. Let's say uh, for for your credit account, you may not call the amount of money that you can borrow for the account as your balance. You may call it as your credit limit, for example. So this one will be incorrect. So the way to do that is to not specifically look at accounts by what exact type of account it is. You do it like this: A dot balance report. So bank should interact with account by printing the return value of this builder method right here. The class bank should not dissect an account to retrieve the balance. It should tell the account to build a balance report. So an example of this one right here, this is from the series of motivational posters made by the artists who compiled these ones right here. The dependency inversion principle. Would you solder a lamp directly to the electrical wiring in a wall? No, you wouldn't do that because that is dangerous and uh, that is a fire hazard. What you should do instead is that you should interact with the socket. This lamp, for example, let's say you have a lamp here. Oops, that's not how you draw a lamp. How do you draw a lamp? Let's say this is a bedside lamp, for example. This lamp right here should not interact with your electrical system using by directly connecting the wires to your outlet, for example. You interact with it through its interface, and the interface in this context is the plug that you use in the socket. This is how the outlet interacts with your lamp. It interacts with it through the interface of this plug right here. And uh, when you do something like this, the outlet doesn't have to know which specific appliance it is interacting with. It knows that it is interacting with an appliance because every appliance has a plug that looks like that. Therefore, it will be able to interact with it, give it, supply it with power in the same way you supply any general appliance with power. This is the source for these motivational pictures right here. And that is all. So if you always internalize, if you commit yourselves into building systems that adhere to these design principles, then it would be natural for you to create systems that will be elegant. If you always adhere to this, you will force yourselves to create systems that work in a maintainable manner, in a future-proofed manner, and in an elegant manner in general. And that is all.